We will try the nines complement procedure now on several other problems to check its accuracy. From 12,250, I'm going to subtract 5,375. 5 is greater than 0, so I have to borrow 1 from that 5, make it a 4, and this becomes 10. 7 is greater than 4, so I have to borrow 1 from that. That becomes a 1, and this becomes 14. 3 is greater than 1, so I have to borrow 1 from that number. 2, it becomes a 1, and this becomes an 11. 5 is greater than 1, so I have to borrow 1 from that 1. That becomes a 0, and this becomes an 11. So I had to modify the minuend extensively. It now reads 0, 11, 11, 14, 10. So I have it in a form where I can now do the subtractions. 5 from 10 is 5. 7 from 14 is 7. 3 from 11 is 8. 5 from 11 is 6. 0 from 0 is 0. So my difference is 6,875. How many operations did I do? Using the textbook algorithm. Number modifications: 1, 2, 3, 4, 5, 6, 7, 8. 8 number transformations. And then I did 1, 2, 3, 4 hard subtractions. 5 from 10, 7 from 14, 3 from 11, 5 from 11. I get my answer. It requires 12 operations to get that answer. Now we'll do it by the nines complement procedure. In the nines complement procedure, if the minuend digits, 5 in this case, is greater than the subtrahend digits, 4 in this case, we have to add a leading 0. Otherwise the nines complement procedure will not work. The number added to 0 that equals 9 is 9. The number added to 5 that will equal 9 is 4. The number added to 3 that will equal 9 is 6. The number added to 7 that will equal 9 is 2. The number that added to 5 will equal 9 is 4. So I have the nines complement of the subtrahend. Now I'm going to proceed to add. I am going to add 94,624 to the minuend. And I'm not going to modify the minuend whatsoever. 4 and 0 is 4. 2 and 5 is 7. 6 and 2 is 8. 4 and 2 is 6. 9 and 1 is 10. So I get a carry into the 100,000s place. It's always going to be a 1, because in subtraction by subtraction, the minuend, the difference is smaller than the minuend. And when we do subtraction by addition, we are adding to the minuend, so we're going to get a carry, a 1 carried over into the next decimal place. The final step in the nines complement procedure is to take that 1, leftmost digit, it's always going to be a 1, add it to the rightmost digit, in this case 4, and I get a 5. So I get 6,875. That is the correct difference. And I got it by addition. And I only converted that to the subtrahend to its nines complement, and then I did 1, 2, 3, 4, 5 easy additions. Does this apply? Does the nines complement procedure work for decimal fractions? What if I put a decimal point there, there, and there. I'll write 12, the minuend again, this time 12.250. Then I'll take the subtrahend and write the 9's complement of it. So it'll be 9, 4, the same numbers as this, 9, 4, decimal point 624. Then I will add it to the minuend. I get 106.874. Then when I add this 1, the leftmost digit, to the rightmost digit, I get 6.875. The same as it would be here, 6.875. So in the decimal fractions, the numbers do not change. The 9's complement procedure, all the numbers are the same. The only thing is we have a decimal point now. Okay? So it works for integer numbers. It works for decimal fractions. Does it work for mixed numbers? This number, translated into a mixed number, 12.250, is 12 1/4. This number, when translated into a mixed number, is 5 3/8. 5.375 translate to 5 3/8. From 12 1/4, I want to subtract 5 3/8. But I'm going to use the 9's complement procedure. So I have to find the 9's complement of this subtrahend, 5 3/8. I'm going to add 3 to that 5. I get an 8. And then I'm going to add a fraction to make this 8 over 8. So I need a 5/8. 5 added to that 3 gives me 8 over 8. And so my number down here will be 8 8/8. 8 8/8 is another way of writing 9. So this is the 9's complement of this subtrahend. So I'm going to proceed to add it to the minuend. But first I must change this 1/4 to eighths. I'm going to multiply 1/4 by 1. That doesn't change the number. 1 times 1/4 is 1/4. And then I'm going to substitute for 1, 2 divided by 2. 2 divided by 2 is 1. And when I multiply this times 1/4, I get 2 times 1 is 2. 2 times 4 is 8. So 2/8 is another way of writing 1 over 4. So now I can proceed to add. 12 and 3 is 15. 2 and 5 is 7, so I get 15 7/8. My last step in the 9 complement procedure is take this leftmost digit, it will always be a 1, add it to the rightmost digit, 5 in this case, I get a 6. 6 7/8. So 12 1/4 minus 5 3/8 is equal to 6 7/8. Is 6 7/8 equal to this decimal fraction? If you divide 8 into 7, you will get 0.875. So they are equivalent. That's how you write 6.875 as a mixed number. So the algorithm works for integer numbers, decimal fractions, and mixed numbers. So it works for all numbers. The special case has a limited range. The subtrahend has to be between 0 and 9, and the minuend has to be between 10 and 18, 10 and 19. So it's the range of the subtraction table, and a student in the first grade could learn to do subtraction by addition once they develop their skills. What else can we say? much easier than doing subtraction by subtraction using the textbook algorithm. We had to do 10 operations versus 5. And the fact is that subtraction by addition is much easier than subtraction by subtraction. There's no borrowing in carries, and we get the correct difference. There may be carries in addition, but that's easy to handle. It's just adding the carry to the next number. All right, that completes it. There's one other question. When we do subtraction by addition, we are doing it the way this handheld calculator and every calculator and every computer on the planet does it that way, and it has done it from its inception because it uses 2's complement arithmetic, not 9's complement as we're using. This algorithm for subtraction by addition is a carbon copy of the way the computer does it. It's not something new.